Hello, thank you for joining me today. My name is Nick Lines, and I'll be discussing my work evaluating topic models in terms of their dimensionality reduction properties. Throughout this presentation, I'll gloss over most of the mathematics and details, but these can be found on the project GitHub by following the link below or the QR code on the bottom left. In that GitHub repository, you'll also find all the code and environment files required to reproduce all of our work. Here's an outline of what we'll be talking about today. I'll briefly talk about what topic modeling is and how topic models fill the role of dimensionality reduction algorithms, and then introduce how dimensionality reduction methods can be evaluated. Then I'll introduce the experiment that I ran. We'll analyze the results and talk a little about the direction that this work should take next. On to topic modeling. Probabilistic topic models have been growing in popularity since their birth in the early 2000s, and for very good reason. They allow a reader to take a huge corpus of text data and discover themes and similarities in the documents that make it easy to find the content that that reader cares most about. We begin with written documents, and we drop from these all syntax, keeping only the information about how many times each vocabulary word appeared in each document. This is sometimes called the bag of words model. We can represent each document as a row vector of vocabulary word counts. This gives us the document word matrix when we put all those row vectors together. It represents the whole corpus using just those vectors. I'm glossing over a lot of details about how you reduce your working vocabulary, including removing low-meaning words and combining terms using stemming and lemmatization, but the basic idea is still here. Now, at its heart, all classic topic modeling does is simply a decomposition of the document word matrix into two-factor matrices. The first one I'll call the document topic matrix. This represents each document as a mixture over a set of latent topics, and those topics get described by the second matrix, which is the topic word matrix. This writes each topic as a distribution over the vocabulary words. Now, typically, topic models get evaluated by reviewing the topic word matrix, making sure that the top n words in a topic's distribution all look similar. For example, the topic data, mining, science, driven sounds good, but the topic data, Toyota, grass, stovetop does not sound good. Various coherence measures exist for measuring the quality of the topic word matrix in particular. However, the document topic matrix, which represents the dimensionality reduction property of this whole topic modeling problem, usually gets ignored during topic model evaluation. This experiment is going to challenge that custom. Quite a few algorithms exist for performing the actual decomposition. The most popular by far is latent Dirichlet allocation. This gets called LDA. Don't let it confuse you with linear discriminant analysis. LDA is a Bayesian approach. It assumes that Dirichlet priors exist, from which the topic word distributions, the document topic distributions, get sampled, and it recovers the parameters to those distributions. An alternative which may have jumped out to you when you saw the decomposition on the previous slide is simply non-negative matrix factorization, or NMF. NMF has the benefit that it is fast, even in its vanilla implementations, and it could be even faster if you use parallelization. In contrast, LDA typically uses Gibbs sampling, a Markov chain Monte Carlo technique that it uses at the topic inference step. This is non-parallelizable, and it can be quite a bottleneck. There's one other option that I'll allude to throughout this presentation. So uniform manifold approximation and projection, or UMAP, is currently the industry standard for dimensionality reduction, especially if you're projecting high dimensional data into a viewable dimension for clustering. It is mathematically designed to learn and preserve topological structures in the data reliably, focusing on local structure more than global. A topic modeling tool has been built around UMAP. It's called Top2Vec. It uses UMAP to reduce the dimensions of an embedded representation of the documents, and then cluster them using HDBScan. This isn't quite like classical topic modeling, since it's producing hard clusters rather than the fuzzy ones NMF or LDA would yield. But it is fast, it's reliable, and it's growing in popularity, so we'll keep alluding to it. Now that we've said topic modeling performs dimensionality reduction, and that I want to measure how well it does that, let's talk about our options for evaluating dimensionality reduction in general. A favorite authority of mine on this subject, Leland McInnes, always says that dimensionality reduction techniques basically fall into either matrix factorization approaches like NMF or neighborhood graph techniques like UMAP. All of these start off with a representation of data in a higher dimension than what we want, and we translate it into a lower dimension. For this discussion, I'll use some toy data that I generated from two Gaussians in a 3D space. I want to reduce the dimensions required to represent this data, and plot the data in 2 dimensions instead. In both embeddings, I could calculate the pairwise distances of each data point pair and get a distance matrix. While the actual values in the distance matrices in the 2 embeddings differ a lot, a good dimensionality reduction technique should preserve the structure of the matrix, which you can see in the heat coloring here. But not all the distances are of equal interest to me. For example, if I'm trying to cluster this toy data, I care a lot more about the nearby points staying nearby under the mapping, and the far off points, they just need to stay pretty far away. So, for example here, the points 1 and 2 need to stay close together for the mapping to keep that same clustering look. But I don't really care where point 4 is in comparison to 1, so long as it's far away. The distances in the new space's distance matrix really only matter to me in proportion to each other. So we could simplify this approach a little bit. Instead of focusing on distances, let's use ranked distances. These ranking matrices that I'm showing now, they show the order of the distance. So these aren't going to be symmetric. Point 2's closest neighbor may be point 1, so there's a 1 at entry 2, 1 in the matrix, but point 1 is closer to point 0, so there is a 2 at the entry 1, 2. Again, what we care about here is that the relative structure of the graph is getting preserved in the new embedding. In this toy data, you can see that does seem to be happening. Very few changes are being made in the ranks between the 2 matrices. Now, using these ranking matrices, we can create what is called the co-ranking matrix. For the co-ranking matrix, each entry KL in the matrix counts the number of times the kth nearest point to some point in the original mapping ended up as the lth nearest point in the new mapping. Here's an example. In this case, the entry 3, 4 is 2, which means that there are 2 times that a point had its 3rd closest neighbor reordered in the new embedding to be now the 4th closest neighbor. And this matrix is really quite useful, and it's not hard to interpret. The upper right half is counts that we'll call extrusions. These are events where 2 points were pushed further away in rank by the mapping. So this kind of error is sometimes called continuity error. The lower left half is usually called intrusions. These are events where 2 points are pulled closer together by the mapping, and that is in terms of rank. This kind of error is sometimes called trustworthiness error. So you can pick a K value that indicates the size of the neighborhoods you want to focus on, and you consider anything in the bottom right quadrant to be trivial, because it represents reorderings in the most distant point ranks. You don't care about that. The areas you are concerned with are the mild intrusions and mild extrusions in the top left. These show significant changes in the local K neighborhoods. So let's focus in on this highlighted K by K square in the top left. For a given K, we could sum up all the entries in this square and divide by K to normalize. This is called the Q nearest neighbors function. By computing the area under this curve, we get a single real number that tells us how well the topological structure was preserved in this mapping, with an increasing emphasis on the more local structures. Now we're ready to talk about the experiment itself. So the question I want to consider here is how well do the out-of-the-box implementations of LDA and NMF compare in 4 key metrics as we walk through the space of options for the number of topics parameter. These metrics are the area under the Q nearest neighbors curve. This checks the dimensionality reduction quality. David Mimno's UMass coherence. This checks topic quality. The runtime of each algorithm, and the reconstruction error. From what we've already seen, the expectation going into this experiment was that we'd see NMF do slightly better in terms of dimensionality reduction and timing, and LDA would be a clear winner in terms of topic quality. And we'll also train a UMAP dimensional reduction model for each topic number just for fun, and we expect to see that these would win out as far as preserving the graphical structure of the data. Now, some more details. The data that we'll use here is a common NLP data set. It's the first 2,000 articles of the CNN daily news feed. You could get this through Hugging Face, for example. We're going to do some simple stemming and produce a single document word matrix, and then we'll feed that into each algorithm once for every t in the range 2 to 200. So every topic number choice that you could pick between 2 and 200. For big parallelizable jobs like this, I really like to use the Python Dask library. It's great for multiprocessing and multi-threading. It takes minimal amounts of code to get going, and it gives you this awesome dashboard that you can use to watch the work get distributed and run. To log the metrics, we're going to use MLflow. It essentially provides model tracking and control, kind of like a Git interface for your model training. It also has a nice web dashboard that you can watch. Now the moment of truth. So first I want to talk a little bit about the kind of output you would get from LDA and NMF. Here is an example. It's common for a scientist who's creating a topic model to guess the correct number of topics parameter by running a PCA over the data and identifying the elbow of the explained variance curve. I did that here. I fit a 8th degree smoothing polynomial to that curve and found the second derivative's roots, and that suggested that the best number of topics is 9. So here's the top 8 words from each topic that you'd recover using LDA or NMF, with 9 as the number of topics parameter. You can see they both look pretty coherent. All right, in terms of coherence, both models did quite well. On the bottom left, you can see a plot showing the mean topic coherence for each algorithm at each topic number between 2 and 200. Higher values are better. LDA does not really edge out as the superior model in this case until you go above 30, 50 topics, which we note is way above the typical guess that we'd start with, 9. In the snapshots above, one for 9 topics, one for 20, and one for 100 topics, you can see a little more detail. We can watch the quality of each topic within a model for that parameter value. For 9 topics, the models are quite comparable. At 20 topics in the middle, you can see NMF gets some poor quality topics, but most of the topics are still similar in quality to LDA's. And finally, at 100 topics, the NMF model is worse on average, but it doesn't witness nearly as bad individual worst-case topics as the LDA model does. So the takeaway here, I guess, is that my hypothesis is not supported. It appears that NMF is not so far off from LDA in terms of topic quality as I thought. Now this is really the main event. This is the area under the Q nearest neighbors curves. This represents how good the actual embedding was. The values can range from 0 to 1. 1 would represent a perfect mapping with no rank changes at all. 0 would represent a totally random mapping. For the first few topic number values, 2, 3, the visible dimensions, UMAP is winning, but NMF soon beats it out and keeps rising while UMAP plateaus. This actually kind of makes sense if you know UMAP, because UMAP is concerned with preserving very, very local structures in projections down to visible dimensions. So as we climb to much higher dimensions for the image space, I guess it's not surprising that NMF really shines. And LDA, of course, climbs very slowly, but it really starts off no better than random. Let's take a closer look at what's happening in the dimensionality reduction. Here's some snapshots of the co-ranking matrices produced by the mappings from LDA, NMF, and UMAP at 9, 20, and 100 topics. You notice the nice defined diagonal for NMF. That's really good looking. A perfect straight diagonal would be the best of all possible scenarios. So NMF is actually doing pretty well. You can see some intrusions in NMF for smaller topic numbers, but it's really overall pretty good. UMAP, you can see, is only really removing the most obvious extrusions and intrusions and sort of shifting the mass of the error down to the trivial region, but it's still very noisy. And LDA is the noisiest of all. And in fact, the biggest gaps that I see are actually occurring in the trivial region, which is unfortunate. In terms of speed, UMAP and NMF are comparable, and, well, LDA is not. It's pretty dreadful, especially in higher dimensions. For higher numbers of topics, you could see the LDA can take up to 4 orders of magnitude longer to run. Also on the slide, you can check the normalized reconstruction error, where 1 is ideal, anything below it is increasingly bad. NMF is designed to approximate the document word matrix perfectly. To approximate well, but it's not really optimized for reconstruction error. LDA, on the other hand, by its construction, is designed to always reconstruct the document word matrix. So we'll see here there's kind of a trade-off that LDA is introducing. We get better topics and assured reconstruction, but really terrible quality mappings. So let's start wrapping up by talking about where we might take this work next. There are a bunch of different dimensionality reduction quality metrics that we could test similarly. For example, the local property metric that focuses a little more like UMAP on smaller K neighborhoods. There's also plenty of other more modern coherence measures that we could introduce and try. The results here are convincing, but to generalize them, we really need to apply them to things other than these English documents of this nature. So we're talking other languages and other kinds of documents. I'm also quite surprised by how quickly UMAP plateaued in quality, so I'd like to look into this more. It sounds like it might be worth trying NMF instead of UMAP for the higher dimension topic models that Top2Vec produces. So with that, I'll conclude. We've got a few takeaways here. The main one is that if you're building smaller English topic models with small numbers of topics, you really seem to be better off using NMF because you get similar topic quality to LDA and better quality mappings for much less work. And even in higher dimension topics number choices, you still need to be aware of what kind of LDA trade-offs you're making. Your mapping quality goes down, you get better looking topics. Thank you for listening. If you have any questions, please feel free to email me and/or stop by the GitHub site. Stop by there anyway to check out the details paper and the code. Thank you very much.